Okay, so I finished about chapter 2, transmission media. Let's continue with chapter 3, key technology. I think we will already learn the WDM structures. We already learn up to OTU, multiplexer, demultiplexer, amplifier, OSC. So we need technology to realize those WDM structure. So actually you can see in our key technology of WDM, we have four very important technology, that is light source, multiplexer, demultiplexer, amplifier, and the supervisory technology. Okay, so let's introduce them one by one. The first one is the light source. Before we introduce the light source, we have some requirements of our WDM light source. We want the technology used in WDM light source has higher dispersion tolerance and output a standard and stable wavelength. Okay. For the higher dispersion tolerance, if the dispersion tolerance is higher, so we don't need too much DCM in our network. So our transmission distance can be longer. You know, the TCM is also one kind of fiber. It must have attenuation. If we can use less DCM, I think the transmission distance can be longer. So that's the requirement of our WDM light source. Which kind of technology we used should follow this kind of requirements. Actually, we have two different modulation can be used in our WDM network. Okay, there's two different modulation. The first one is non-coherent modulation. Okay, the second one is coherent modulation. Okay, actually, the first one, non-coherent modulation, is used for low bitrate service, such as under 10G. For coherent modulation, this is for large bitrate service, such as 40G, 100G, like this bandwidth. Okay, and in this non-coherent modulation, we also have two different types. The first type is direct modulation. Okay, the second type is belong indirect modulation. Okay, so let's see the direct modulation firstly. Okay, it also can be called internal modulation. It is used to directly modulate the light source signals. This method determines the stress of the laser output light wave by controlling the current injected to the laser. Okay, and commonly the direct modulation and normally direct modulation or common G.652 fibers can use to carry the service when less than 2.5 G bit per second, cannot higher than this kind of speed. And the distance should be less than or equal to 100 kilometers. So because these features, so it generally applied to use it in CWDM system. Okay. And another two is belong the indirect modulation, EA and MZ. EA modulation does not directly modulate the light source. In this modulation method, an external modulator is used on the output path of the light source to modulate the light wave. This modulator is equivalent to a switch. Okay, and the laser of EA modulation is complex. The loss is high and the cost is high. However, EA modulation has a small modulation frequency chirp and can be applied to a system with transmission range of 2.5 G bit per second or higher and a transmission distance of over 300 kilometers. Okay, that is the EA modulation. But about the MZ modulation, the MZ modulator splits the input light into two equal parts and directs them on its two optical passes. On the two optical passes, electron optical material is used and the refractive index of the material varies with the stress of the external feed electrical signals. As the refractive index changed on the optical path will cause a change in the signal phase. The combined optical signals at the output end of the two optical paths is a coherent signals with very stresses. In this manner, information carried on electrical signals is transformed onto the optical signals, and then the electrical signals are modulated based on the stress of the optical signals. The frequency chirp of the separated external modulation laser can be equal to 0. So compared with the EA modulation laser, the separated external modulation laser has high cost. So MZ has good performance than EA, but it will make you cost more money for MZ modulator. Okay, so that's the direct modulation and indirect modulation we used in under 10G service. Okay, but after 10G, we used some new modulation, that is technology, that is coherent modulation. Okay, so what is coherent modulation? Check this out. Actually, our light transmits with a lot polarized direction, but a lot of this polarization is useless in the sync direction. In the sync direction, we only need one polarized direction. It can be anyone. Okay. So after we consider about this information, so we can use different polarized direction to carry different bytes and transmit at the same time. Okay, so we can this one we call PDM, polarization division multiplexing modulation. Okay, so it has a lot of different steps. In the first step, PBS, which is the polarization beam split, splits the laser light into two polarization, X pole and Y pole. And these two different polarization direction is perpendicular. And then after the laser at the transmit end is divided into two parts in polarization X and Y, QPSK or BPSK modulation is performed on the two polarized light X and Y. The polarization multiplexer combines the modulated optical signals in polarizations X and Y into one optical fiber, and then the signals are multiplexed and amplified for optical cable transmission. Okay, so it's kind of like this way. We can use different polarization, carry different bit, different bytes, and mix them together, transmitted by the same frequency. So the procedure will be like this way. Okay, actually, in PDM, one light is divided into two polarizations, and the signal carried by the light is then modulated onto the two polarizations. This procedure is equivalent to splitting a data stream into two parts, reducing the data range by half. Okay, and for QPSK, phase equals to 2 bits, which has the same effect as to divided data into two parts, and therefore the range is reduced by half. Okay, for 100G signals, actually 100G in transmission network, the actual bit range is 112G bit per second. The actual data ball range is only 28G ball. It's kind of this way, right? After the signals arrive at the sync station, a local laser that has the same frequency as the received signals is used to implement coherent process between the laser signals and the received signals to restore the amplitude, phase, and the polarization state information from the received signals. We'll do the reverse process in substation, right, this way, and detect which kind bit be carried by these two different polarization, right, and got what we transmit by the PDM modulation. It's like this way, okay, and we can compare these four different modulation. The direct modulation, the dispersion tolerance is very small, only 1200 to 4000, okay, picosecond per minute. AC is for 2.5 series. Okay, for EA, it's almost 7,200 to 12,800. Okay, for MZ, because cost too high, so we got good performance. The dispersion tolerance is 12,800. Okay, but for coherent modulation, you don't need to care about dispersion anymore, chromatic dispersion anymore. The dispersion tolerance is 40,000. Actually, for the newest coherent technology, the dispersion tolerance can be 150,000. You can do a mass calculation. For G.652 fiber, every kilometers you will have 17. So with this coherent technology, how much distance you need to do the dispersion compensation? Almost never, right? So the cost is from midair to the very high. Okay, okay. And the wavelength stability, you can see coherent technology is very good. With in the direct modulation, the wavelength stability also good, right? But the direct modulation is the baddest, right? Okay, so that's all the modulation we used in our WDM network, right? So let's check another very important technology, optical amplifier. The optical amplifier can be divided into rare earth ion doped and non-layer optical fiber amplifier. Rare earth ion doped optical amplifier amplify the optical signals using the simulated radiation mechanism, and non-layer optical amplifier amplify the optical signals using the non-layer effect of optical fibers. Among the optical amplifier, Erbium doped fiber amplifier and the Roman fiber amplifier are being used a lot, practical, right? So let's check the EDF. The EDFA urban doped fiber amplifier, which is widely used in our real network, okay? But RFA, Roman fiber amplifier, used in some special places. It's not widely as EDFA. For some special places, RFA is very good, okay? OS do not need to convert optical signals to electrical and then convert electrical signals back to optical, right? This feature helps form two advantages of a regenerator of signals. The first one is OS support any bit rate and signal formats, and simply amplify all received signals. This attribute is generally described as that OA are transparent to any bit range and signal formats. The second one, OS not only support amplification of single signal wavelengths, which is similar to a regenerator, but also support optical signals amplification within a certain wavelength range. In addition, only OS support PDM and WDM network with multiple bit range, varying modification formats and different wavelengths. Okay? Actually, WDM technology plays an important role in optical fiber communication only after OS, especially EDFAs, become available. Currently, EDFA is the most popular optical amplifier. It has transformed the theories of WDM and optical network into reality. Let's check them one by one. What is EDFA? What is RFA? Okay, so before we introduce the principle of EDFA, we should know one basic knowledge, that is, outer electrons of erbium ions has three different energy level. This one is E1, ground state. This is a very stable energy level, and the second one is E2, is mid stable state, and the E3 high energy level, okay, state. And check this out. Normally, all the electrons are running on this E1 ground state. When a high energy bumping laser is used to simulate an urban doped fiber, a larger numbers of bound electrons of the urban ions is simulated from E1 to E3. However, E3 is unstable, uh, so all the electrons will change the energy level from E3 and drop to E2. E2 is a metastable energy level at which a particle can exist for a long time. The particles simulated by the bumping laser continuously assemble to E2 in non-reactive transit mode, achieving distribution for population inversion. And when optical signals with a 50-50 nanometer wavelengths traverse the EDF, Particles at the E2 level are stimulated by the signal photons. Then those particles transit to the E1 level in the stimulated radiation mode and generate photons the same as